Welcome to today's Explainer. I'm so stoked you're here. We are jumping right into Physics 101 today to decode something absolutely fascinating, the standing wave. We're going to take some abstract physics and math and show you exactly how it creates the real-world sounds and structures we experience every single day. So picture this. You pluck a guitar string. Why is it that some frequencies produce these massive, gorgeous vibrations that just ring out for seconds, while others literally disappear the second you try to play them? It's not random. The string is actually selecting specific frequencies based on the laws of physics. And the secret to the whole shebang? Standing waves. Here's our roadmap for today's session. First, our Welcome to Physics 101. 2. How standing waves form. 3. Anatomy, nodes and antinodes. 4. Guitars, resonance, and harmonics. And 5. Standing versus traveling waves. All right, part 2. How standing waves form. The rules of superposition. Okay, to really get standing waves, we've got to talk about the principle of superposition. As our source material perfectly puts it, waves don't know about each other. When two waves are moving through the exact same medium, say a single guitar string, they don't crash and bounce off each other like cars on a highway. No, their displacements just add together algebraically. Where they overlap, they combine. Let's break this down step by step. Imagine wave A is traveling to the right, and wave B is traveling to the left. Same frequency, same amplitude, same string. As they cross paths, superposition happens at every single point. Step 3 is where it gets crazy. Where the waves are perfectly out of phase, meaning they are doing the exact opposite thing, they cancel each other out. Completely. Forever. These become fixed points. On the flip side, in step 4, where they perfectly reinforce each other, the amplitude literally doubles. Notice that dotted line right in the center. That is your resultant standing wave. It's the literal mathematical addition of those two traveling waves. Because the incoming and reflected waves have the exact same frequency, the interference pattern doesn't move left or right anymore. It's totally stationary. The wave itself is moving up and down in time, sure, but its peaks and valleys, they're locked completely in place. Moving on to part 3, anatomy, nodes and antinodes, or as I like to call it, the geometry of stillness. You're going to need 2 crucial vocab words for this, and here's the first one, a node. A node is a point on the medium that has absolutely zero displacement, all the time. Thanks to complete destructive interference, these specific spots, whether on a string or inside a pipe, stay perfectly still forever, as long as that wave keeps going. And vocab word number 2 is antinode. This is the exact opposite of a node. We're talking maximum displacement. This is where those traveling waves are perfectly teaming up in constructive interference. So if your original wave had an amplitude of, say, A, the antinode is swinging wildly back and forth with an amplitude of 2A. Look at how perfectly symmetrical this geometry is. You can clearly spot the nodes where the wave crosses the center line. Those are your points of zero motion. And the widest, fattest parts of those loops, those are your antinodes. And here's a golden rule to remember. Adjacent nodes are separated by exactly half a wavelength. Same goes for adjacent antinodes. This super predictable spacing is actually how physicists measure wavelengths with such incredible precision. Oh, actually, real quick before we move on, we have to talk about phase. Every single point within a single loop, meaning the whole space between 2 adjacent nodes, oscillates in phase with each other. They rise together, they fall together. But jump across a node to the adjacent loop, and those particles are exactly in antiphase. So when one loop goes up, its immediate neighbor goes down. It's like a perfectly choreographed dance. All right, section 4, guitars, resonance, and harmonics, bringing it to life. So let's circle back to that guitar from the beginning. When you pluck a string, you're sending out a traveling pulse. That pulse races down the string until, bam, it hits the nut or the bridge of the guitar. Now, because those ends are tied down super tight, they are forced to act as fixed boundary nodes. The pulse hits the boundary, flips completely upside down, and bounces back. These reflected waves then mix with new incoming waves. But, and this is key, a stable standing wave pattern will only survive if it perfectly fits between those 2 fixed ends. We call these our resonant harmonic frequencies. So what actually determines the speed of that wave? Well, for a string, wave speed, which we call v, is governed by this beautiful little equation. V equals the square root of t over mu. T is the tension, literally how tight you crank the tuning peg, and mu is the linear density, which basically just means how thick and heavy the string is. That's exactly why those big, thick bass strings give you much lower notes than the skinny treble strings, even if they're cut to the exact same length. And here's where the math really scales up. The lowest possible frequency that fits on the string is the fundamental mode, or the first harmonic. The formula is just wave speed divided by twice the length of the string. So for an open E2 guitar string, that spits out 82 Hz. But check this out. The string doesn't just vibrate at that fundamental frequency. It actually vibrates in clean, whole number multiples at the exact same time. The second harmonic fits 2 half wavelengths perfectly onto the string, which doubles the frequency to 164 Hz. The third harmonic triples it to 246 Hz. All of these standing waves are stacked on top of each other simultaneously. That is what gives a guitar its rich, complex tone. Section 5. Standing versus traveling waves, the grand contrast. This right here is probably the most profound difference in all of wave physics. A traveling wave, like sunlight or a ripple moving across a pond, progresses forward. It's actively transmitting energy from point A to point B. Every point along that wave will eventually feel the exact same amplitude. But a standing wave, its shape is completely locked. The nodes sit perfectly still, while the points right next to them are swinging with massive amplitudes. And the biggest difference of all is the energy. A standing wave does not transmit energy through space. It just sloshes it back and forth locally between the nodes and antinodes. That localized energy is exactly why playing a chord doesn't physically yank the guitarist into the guitar. All that massive vibrational energy is just safely trapped right there on the string. Which leaves us with a pretty mind-bending thought to wrap up with. We've just seen how standing waves perfectly localize energy on a simple acoustic guitar, turning chaotic vibrations into fixed, unmoving patterns. But physics doesn't just stop at music. If standing waves can lock energy into these specific, quantized harmonic states without transmitting it away, how might that exact same sloshing energy explain the fixed, highly stable orbits of electrons in the quantum states of literally every atom in our universe? Seriously, think about that. The exact same math that makes your favorite song resonate is what's holding the actual fabric of reality together. Thank you so much for joining me for today's explainer. Keep wondering, keep calculating, and I'll catch you next time.